Here we'll go through an example of solving an example of a heat pump. So we see this question 1146 from the textbook. We're using refrigerant 134A as the working fluid operating between pressures of 100 kPa and 200 kPa. We're asked to find the coefficient of performance and the rate of heat supplied to the evaporator. So we'll draw this temperature entropy diagram as we always do. We'll draw in the saturation curve. And we'll draw our ideal heat pump cycle on the graph. So from 1 to 2 is the compressor, from 2 to 3 is the condenser, 3 to 4 is the expansion, and 4 to 1 is the evaporator. So we have heat going in at the evaporator, QH going out at the condenser, and work going into the compressor. And we'll draw on our two operating pressures. So we'll start at point 1. We know our pressure, and we know that this is a saturated vapor. So we can look up the values of entropy and enthalpy in the tables for the refrigerant. So here's table A12 from your book. We'll find 200 kPa, and we'll find Hg and Sg. And we'll write them down here on our solution. And the entropy is 0.9377 kilojoules per kilogram Kelvin. From 1 to 2 is ideal, so we're considering it a constant entropy process. So we know what our entropy is from looking it up before. And we know what the pressure of state 2 is. So we'll go to table A13, which is the superheated refrigerant table. And here we have to interpolate. So we know it's between 40 and 50 degrees. So we'll look up our enthalpy and our entropy values that we'll interpolate between. So H2 is equal to 0.9377 minus 0.9179 divided by 0.9525 minus 0.9179 multiplied by the difference in enthalpies from the table values plus 271.71. So H2 is equal to 277.98 kilojoules per kilogram. H3, if we look at our graph, is a saturated liquid. So we can look that up at the pressure, 100 kPa. HF is 107.32. So we'll write that down in our solution. And we treat 3 to 4 as a throttling process with constant enthalpy. So enthalpy at state 4 is equal to the enthalpy at state 3. So in summary, here's our 4 enthalpy values for the cycle. Now we need to find the mass flow rate. We know the total work done by the compressor, and we can equate that to the mass flow rate multiplied by the specific enthalpy difference. We know the total power input is 6 kilowatts divided by H2 minus H1. And we enter these values into our calculator, and we get a mass flow rate of 0.179 kilograms per second. So now we want to find QL, the heat going into the evaporator. That's equal to the mass flow rate multiply by the difference in specific enthalpy. We'll plug in these values, enter them into our calculator, and we get 24.5 kilowatts. The last part is to find the coefficient of performance. So for a heat pump, that's equal to QH divided by Wn. QH is H2 minus H3, Wn is H2 minus H1. We'll plug in these numbers. Put them into our calculator, and we get a coefficient of performance of 5.09. So here's a simple example, and you can use it to do something more complex later on.